Hello everyone. I am Indrajyoti Gaine, and presently I am pursuing my PhD at Department of Mathematics and Statistics, IIT Kanpur, and I am a PMRF fellow right now. And I have cleared my CSR NET with 108 rank. Okay, so it is continuation of the previous three lecture of set theory, and today we will cover the rest of the part. So in the last class we have discussed about the okay okay it's enough. Okay, in the last class we have discussed about the union and intersection of two set, and also we have checked that how Venn diagram helps us to verify all these things. Now in this today's class we will see some properties of this set operations. Okay, so some properties of set operation. Okay, so at first let A and B be two set. Okay, let A, B, C are three sets. Then first A union B, this is equals to B union A. First of all, this how? Let's take with Venn diagram. So first A union B. Suppose this is our A, and this blue one is our B. So what is A union B? A union B is the whole part, right? A union B is the whole part. Okay, this is our B, and this is our A. So what is about A union B? The whole part, right? And what about B union A? Again the whole part. So automatically A union B and B union A both are same. Similarly, we can write A intersection B. This is equals to B intersection A. Why? Again check by Venn diagram. This is our B set. This is our B set, and this is our A set. And what is the common part? This is the common part. So this is the A intersection B, and also this is the B intersection A. So these two same thing are clear from Venn diagram. Okay, next. And now note that this square box represents the universal set. We have already discussed the universal set in the last class. So this set, this square box represents the universal set. Okay, next property, A union the universal set. This is obviously universal set. Why this is so? This is our U. U means the all the set, and this is suppose our A. Okay. Suppose this is our A. Now this A is subset of U. Okay, and one remark, we have already discussed this thing last class, that if A subset of B, then A union B is equals to B. Now in this case, from Venn diagram and from definition, we know that A subset of U, which implies A union U is equals to U. And it is also clear that see that because A subset of U, So whenever we are taking union of all these things, we will get the whole U. We will get the whole U. Now, what about A intersection U? This will give the set A. Why? See the Venn diagram again. U, and this is our A. So this set represents A, and this is subset of U. And already we have another remark in the last class that if A subset of B, then A intersection B, this is equals to A. So clearly this thing is true. Same as this thing. Okay. So the what about intersection? Intersection is this part. Okay. Now the third property. So we have two property for union, one property for intersection. Okay. Now what about phi? A union phi. That means we are taking union with empty set. So by definition of union, we know that this is the collection of all elements which are either in A or B. That is either in A or phi. Now, what are the element of phi? There are no element. So A union phi is equals to A. Similarly, what about A intersection phi? This is the collection of all these elements which are common in A and B. Now phi contains no element. So what are the common element? No element. So A intersection phi equals to phi. Now the fourth one. This is called the associative law. Associative law. What is that? This thing saying A union B union C equals to A union B whole union C. And same for intersection. A intersection B intersection C, which is equals to A intersection B intersection C. And we can use the Venn diagram to prove this. At first, check for union. So this is our A. In this green, in this blue, this is our B. And in yellow, this is our C. Okay. So in blue, this is our B. In green, this is our A. In yellow, this is our C. So what about B union C? B union C means the whole part, like this thing and this thing, whole union B union C. And what about A union B union C? A, if you union with this thing, then we will get, I think, this. Similarly, if we do the same thing like A union B and then union C, we will get the same thing. So there are no difference. So we can, for our prospective use, we can write like this. Now, what about intersection? This is a little bit interesting because there are two kind of thing we will get. Okay, for what and for what is this? Let's draw this first. In the union case, the both images are same, so you can't differentiate the both side image. But in case of intersection, you can correctly differentiate between the two images. Okay. So this is our A set. This is our B set. and this is our C set. So also draw here also Venn diagram. This is our A set. This is our B set, and this is our C set. A. Okay. So what about B intersection C? B intersection C implies this portion. Okay. And now, if we take the intersection with A, what we will get? We will get the green part. We get this part only. Okay. Okay. Now, in case of this thing, what we will get first? First, we will do A intersection B. So this thing is, now we are taking the intersection with C. So we will get this green part. Okay. So clearly you can see the both sides shades are same. Like if left and in right, whatever we are obtaining, both are same. But the difference is their construction. How we have got the two set. Okay. In the first case, we are first taking intersection of B and C, and then taking the intersection with A. But in the second case, we are taking intersection with A and B, and then taking intersection with C. Okay? And in all the cases, we are getting the same set. This is called our associative law. And another important thing, okay, A union A, this is equals to A, and A intersection A equals to A. That is, any set operation with itself will give us the same set. Okay, either it is union or intersection. Okay, now come to the distribution law, distributive law. Distributive law. Distributive law. Okay. Okay. Distributive law. So this thing is right. Okay. A intersection B union C. This is equals to A intersection B union A intersection C. And this is the first property and the second property. A union B intersection C, which is equals to A union B intersection A union C. A union C. Okay. So let us check this through Venn diagram. It will be better to prove this thing using the Venn diagram, and then we can see few examples to verify all these things. Okay. So Venn diagram. First, for the first one, for left side, and this one for right side. So in similar way, we will draw all the set A, B, and C. This is our A, green. This is our B, and this is our C. Okay. So first of all, take B union C. What about B union C? We will get this white portion first. Okay, this is our B union C, and now we are taking the intersection with A. So what part we will get? We will get this part, right? We will get this red part. Okay, and what about the right portion? Let us draw it first. This is our B, this is our C, and this is our A. Okay, so first of all, first check A. What about A intersection C? A intersection C denotes this thing, this part, this white part. And what about A intersection B? This thing denotes this white part. So together, if I take the union of these two sets, we will get again the red portion, right? I'm not making it whole red. Just check that these two sets are same. So you can by seeing my drawing, it can seem like they are not same, but yeah, they are same set. They are like by my drawing, they are not looking like same, but yeah, these two sets are same. Okay, so by this thing, we have proved that one is equal. Like A intersection B union C equals to A intersection B union A intersection C. Okay. Similarly, for 2, we can prove this. What about A union B intersection C? This is all U. Okay. Green, blue, B, and yellow is represented with C. A. Okay. Similar way. A. This is your B, and this is our C. Okay. So what about B intersection C? B intersection C means this part, this white portion. And what about A union B intersection C? Like we're taking union with this A. So we are just drawing it as a red line. This part, the whole part. And what about this thing? A union B. A union B means okay, this part, this white part total. And what about A intersection A union C? A union C means this part. So please check that. Again, we are obtaining the part this part is equal, and this part. So we are obtaining this part. Similar like this. Okay. So yeah, we are now clear that these two sets are same. A union B intersection C is equals to A union B intersection A union C. Okay. Okay. So this is our distribution law, and these are very important to properties of set union and intersection. You can use it for set operations, and many important questions comes in state level exam or joint entrance itself. So okay. So take one example to check all these things. Let us take A equals to 357 9 11. B equals to 7 9 11 13, and C equals to 11 13 15. D equals to 15 17. Okay. Your question. Okay. So first of all, what about A intersection B? Okay, what is A union B? This is 3 5 7 9 11 13. And what about B union A? The same set. 7 9 11 13 3 5. And this thing gives us that A union B is equal to B union A. Okay. What about A intersection B? A intersection B. So what are common element in these two sets? 7 9 11. And also check that this is same as B intersection A. Okay, so we have verified both the two things. Now what about D intersection D? This is nothing but 15 and 17, and also this is equals to D union D. Okay. Now what about A union sorry, not union, A intersection. Let's check A intersection B union C. What is this? So we know we can do in both way. We can check the both way. So first, find what is A into B union C. What is our B union C? B union C represents our the collection of all these sets like 7 9 11 13. 7 9 11 13 15. Now we are doing what? A intersection B union C. So what is our A? A contains 3 5 7 9 11, and what contains 7 9 11 13 15. So if I take the intersection, we will only have 7 9 and 11. We will only have 7 9 and 11. So this is one way. What about the another way? We have already used the we have already proved distribution law. So let us check what we get by distribution law. Union A intersection C, right? From the distribution law we know this thing, right? So let's verify. What about A intersection B? A intersection B implies 7 9 11. 7 9 11. What about A intersection C? Check that A intersection C contains only one element, that is 11. Right? So this is equals to 11. Now if I take A intersection B union A intersection C, we will get 7, 9, 11. So it's verified. A union B intersection C. Sorry, not like the ulta. It's reversed. Okay. A intersection B union C. This implies A intersection B union A intersection C. Okay. So we have verified this thing through an example. In similar way, we can find other states also. Like if I do other operations, and we will do equal reapply all the operations for the other states for other combination like A, C, D. Like if I do the same procedure with D, then also it can be done. So this is the example of NCERT book 6, question number 6. Example question number 6 and exercise 1.4. exercise 1.4. So you can check this question, and there are few more questions about asking other opposite operations. So you can verify all those things. Okay, so let us verify another thing, the same from the same question. That is, what about this thing? A intersection B union B intersection C. What about this? So one may get confused here because we know about distribution law, but what about this? Like here the first element is A intersection B and second element is B intersection C. So we can apply the distribution law here by just using the property that A intersection B equals to B intersection A. So this thing can be replaced as B intersection A union B intersection C, which gives B intersection A union C. Okay, so don't get confused whenever the things are looking little different. We can use distribution law even though they are not in the format of distribution law. Just you need to rearrange the terms accordingly. Okay. Now come to the next topic. This difference of two sets. Difference of two sets. So what we understand by this term difference? So difference usually saying that we are subtracting some element from some element. Like whenever we subtract 15 minus 5, we get 10. For this, we can take an example that there are 15 mangoes in a, or 15 mangoes in a container. Okay, how many is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11, 12, 13, 14, 15. Okay. So here we have 50 mangoes in a container or in any pot, and we are putting 5 particular mangoes from here. So just cut or erase those mangoes, like 1, 2, 3, 4, 5. So how many mangoes we are left with? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So we have 10 mangoes right now. So similar way, we subtract 15 minus 5 equals to 10. Now we are applying this this subtract operation on sets. Like if A and B are two sets, then the question is, can we define this thing? What about this set? So we are defining this set like this. Just look at the Venn diagram, then we will see a definition. This is our A. This is our A. And this is our B. This contains the blue lines. Okay. Now what about A minus B? So A minus B is denoted like this. Yeah. This is our A minus B. This is our A minus B. So I hope you understand the photo. I mean the diagram we have drawn. So we are just eliminating those elements of A which are common in B. Okay. So we are subtracting, eliminating those elements of A. So in this set, we are eliminating those elements from A which are common in A intersection A and B, which are common in A and B. So in particular, we can write this like this. A minus B. This is nothing but A minus A intersection B. Okay. So by this we can write the same thing, because whenever we are subtracting B, this is nothing but that we are subtracting the common elements from them. The common elements of A and B, and we are subtracting this from our set A. Okay. So what is the definition? So by definition is saying, I can write in a different color. So by definition saying is, the difference of the sets A and B is the set of elements which are belongs to A but not belongs to B. That is, if we do it by set notation, then this is the collection of all those x such that x belongs to A, but x not belongs to B. Okay, so by this notation we can define A minus B. And also you can see this, we have done the same thing. We have eliminated those elements which are in B and A both. So we are only including here, we are only including those elements which are only in A, not in B. Okay. Okay. Okay, so take one example. Let us take A equals to 1, 2, 3, 4, 5, 6, and B equals to 2, 4, 6, 8. So what about A minus B? A minus B means we are eliminating those elements which are common in A and B. Okay. So first of all, check what are common in A and B. That is, what are in A but not in B. So let us do it by this process. Okay. So what about A minus B? First check the 1. 1 belongs to A, but 1 not belongs to B. So 1 can be here. And what about 2? 2 belongs to A, but 2 belongs to B. So 2 will not be there. What about 3? 3 belongs to A, but 3 not belongs to B. So 3 will be there. Again, 4 belongs to A, but 4 not belongs to, also 4 belongs to B. So 4 will be not there. What about 5? 5 belongs to A, but 5 is not belongs to B. So 5 will be there. What about 6? 6 will not be there. What about 7? Okay, no. 7 is not belongs to A. So we are not bothered about those elements. So this is the set A minus B. Check that. This awesome. Check. 1 belongs to A, but 1 not belongs to B. Okay. 2 belongs to A, 2 belongs to B. 3 belongs to A, 3 not belongs to B. 4 belongs to A, 4 belongs to B. 5 belongs to A, 5 not belongs to B. So by this thing, we will only include these elements. This, okay, only letter 6. 6 belongs to A, 6 belongs to B. Okay, so we will only include these elements and we will exclude these elements. Okay, so by this process we are getting A minus B. Now also check this thing. What about A intersection B? This is equals to 3, sorry, not 3, okay, 2, 4, 6. And what about A minus A intersection B? By similar process we can do, and we will get 1, 3, 5. Okay, so these two sets are same. A minus B equals to A minus A intersection B. Okay, so we will use this definition. We will use this definition to find the set A minus B. So let us take another example. Example 2. So let x equals to A, B, C, D, and y equals to F, B, D, G. So what about x minus y? Check that A belongs to, check, first check. Okay, check. A belongs to x, A belongs to y? No, A not belongs to y. So A will be there. Acha. B belongs to x, but B belongs to y. So B not will be there. C belongs to x, C not belongs to y. So C will be there. What about D? D belongs to x and D also belongs to y. So D will be not there. And there are no other element in x, so bracket will be closed here. So this is our x minus y. Okay, what about y minus x? Again check. Check. F belongs to F belongs to y, F not belongs to x. So F will be there. What about B? B belongs to y, B belongs to x. What about D? D belongs to y, D belongs to x. What about G? G belongs to y, G not belongs to x. So G. Okay. So if we enter this, we will enter this and enter this, but not this. And similar way, we will not allow this two element and we will allow these two elements. And thus we can find x minus y and y minus x. Okay. Now we have discussed the difference between two sets A and B. Okay. So if A and B are two sets, we know about A minus B. So one thing, if B subset of A, what if B subset of A? So take one example. Let A equals to 1, 2, 3, 4, 10. And what about this B? B equals to 2, 4, 6, 8, 10. Okay. So clearly you can see that B subset of A. Now what about A minus B? A minus B. This is equals to 1, 3, 5, 7, 9. Why? Because of use the definition. Use the definition of A minus B and you can get this thing. Now, if we consider this A to be universal set, if we if we consider the set A as a universal set, then A minus B, universal set U, then A minus B, this is nothing but U minus B, and it is denoted by B prime and called complement of B. What is this called? Complement of B. Okay. So first of all, take one example. So let us take the students of all class 11. All students of class 11 as the universal set, and say given set is the set of all boys. Okay. So example, let's see with the set of all students of class 11. Okay, and B with the, okay, this is called U because this is our universal set. B is the set of all boys of class 11. So what about B prime? This is the set of all girls in class 11. Set of all girls in class 11. This is denoted by B prime. This is nothing but U minus B. Okay. So this is called the complement of the set B. And where the complement we take? We take under the universal set. So here, if I discuss about this problem, then A minus B is the complement of B in the set A. So this is the complement of B in the set A. And for this condition is very important. We need this condition to claim that this is a complement. If this condition doesn't hold, then we can't say that this set is a complement of the set B in the set A. We can't claim that thing. So for this, to claim this complement, we must need this containment relation. Okay. And whenever this A set is extended by universal set, then we call it is a complement, because in case whenever we take the universal set, it must contain the subsets. So all subsets, like whatever we are taking, like subset, the universal set must contain that subset or that set. So therefore, that complement must be their element, must be that subset of the same thing. So this containment relation will be held automatically. So we can straightforward say that B complement exists. But whenever B is not a subset of A, then we can't claim that A minus B is a complement of our A, complement of our B.